Welcome back, students, to our next lecture session on main memory. So last class we were discussing about main memory. We saw what is the contiguous memory allocation. We saw what is swapping. So let's revise what is swapping and then continue our lecture on contiguous memory allocation and paging and segmentation. The last three sections of our Unit 4, first part. So we understood swapping. We understood that in the main memory we have a lot of programs for increasing the degree of multi-programming. We need to have multiple processes in the main memory, and for that we have to take care that any process that requires memory and any process that is in waiting state has to be removed out from the main memory temporarily. It has to be removed from the main memory temporarily, and we get in the new process or another waiting process which is ready to execute. We bring it back into the main memory. So that is swapping. So we understood that in the main memory and your hard disk, part of your hard disk is working as an extended memory or storage block or blocking store. So in this is the dead memory. Why we call it as a dead memory? Because here we have the OS. This OS is the resident OS, and our process will be, this is the user space. So this space is allowed, in this processes residing for execution, and this will be going to your central processing unit, wherein you have certain registers, and you will have a processor. The processor will use the execute your program, and between the main memory and the hard disk. So that technique is called as swapping. So extended memory processes that are in waiting state, and we get back the processes that are ready to execute into the RAM. Only the processes that are there in the main memory can get attention for execution. So this is what we have understood till now. So then we have started our discussion on contiguous memory allocation. So let me go to the slide. Yes. So we were talking about swapping in the last class. So we understood that swapping is a process that we bring a processor into main memory, and the main memory processes which are in waiting state, we put them into the backing store and then come and get it back when it is ready for execution. This we have understood with the scenario of round robin, wherein the processes, if there are more processes that are in queue for execution, then if there is no space for storing all those processes into the main memory, we put them into the backing store, and hence we do a round robin scheduling. One process which is executing till the last process that is executing, we go on, and if there is less space, we remove the process which has finished just execution, we put it into the backing store, and that which is waiting for execution will be brought back into the main memory. And if we have priority scheduling, then we use the term roll in and roll out, wherein the higher processes roll in and the lower priority processes are rolled out to the backing store. So we have a ready queue. So for the processes that are waiting store or who are waiting here for the main memory execution, for all that we have a ready queue, and processes which we need to execute are brought from the secondary store to your primary memory or the main memory for execution. So that is what we understood in the last class. we have understood that processes, you need to take care of the issues in swapping. If the process is waiting for an IO, you should not remove such process from the main memory. If you want to remove such processes from the main memory, you'll have to wait for it to finish the IO, and when it gets the IO, that time you remove the process. Or you can do one more thing, is you can use the operating system's buffer memory to get the input from the input devices, or whatever IO has to be done, whatever status it's waiting for, then you get that to the operating system buffer, and the operating system will intimate the process that this is what has happened with the IO. So if the input has come in, it will deliver the input to the process. If there is an output, the status of that output, whether it was successful, not successful, whatever error was there, that is provided to your operating system, from a operating system to the process. So in that case, the system can be removed. You also need to take care that the memory requirements can be less or more. So it can sometimes reduce the memory, processes can reduce the memory, and processes can increase the memory. So in that case, they always have to intimate the operating system with the request memory and release memory. So this way you all will come to know what is the actual memory that is utilized by the process at a given time, and you all can only swap that process because the time that is required to swap a process is also need to be considered. So here yesterday we discussed that 100 MB of process is there, and the rate at which it transfers is 50 MB per second. Then the time that is required for 100 MB data to be transferred to the secondary store will be 2 seconds, and to get it back into the memory is another 2 seconds. This is without considering the latency. Latency is delay in communication and in execution. So without that, only it takes 4 seconds of time for getting a process out of the main memory and getting it back for execution. So if there is again a latency of 8 seconds, it is 4.08 will be 008 will be the amount of time that it will take. Sorry, if 8 milliseconds, then it will be 1640. For one transfer, it is 0.8 milliseconds. It is 8 milliseconds. So that means for to and fro, it will be 16 milliseconds. So we have to consider that. So you try to reduce, if there is less, process size is less, then it is lesser time. If process size is more, then it takes more time. So for example, if I and make it a 1000 MB file, then this will take 40 seconds. Are you all understanding? So that's how as the size of the process increases, the time required for transferring also increases. So context switch timing, that's what we talked about. So always transfer IO or kernel space then to the IO. This is what we discussed, that you allow the IO processes to use the operating system buffer. This also doubles the buffering also. So that is what is here. So we discussed all this in the last class. Now, and we started with contiguous allocation. So we will start again with the contiguous allocation today. So contiguous allocation is allocation of memory. So if your file is of 100 MB, it has to be given from the main memory. If your file is of 200 MB, then you have to search for a 200 MB space and allocate it. So initially, when the process are not loaded, when you start a program, there is no process in the system. Initially, there are no processes in the system. In the main memory, there are no processes. When you start, only the resident operating system will be there in the memory. Then, when you say execute one program, that one program, okay, whatever space it requires, that much space will be allocated to process 1. The next process that comes into the picture, you all will allocate process memory to that. The next process, whatever it requires, less or more, you all will allocate that. So this much space is remaining now. Supposing if this is only and another process P4 comes with a request of 200, suppose 260 MB. process size is 260 MB. Can you allocate space in main memory for this? Because contiguous memory allocation is required. What do we mean by contiguous allocation? One full block. 260 MB block is required of the main memory. Because only 100 MB is left over in the main memory, we cannot allocate memory for P4. So P4 goes into waiting state because it is not having sufficient memory. Operating system is not having the resource requirement. So when any of these finish its execution and leave 300 MB, this P2 finishes and it exits from the system. If P4 is waiting state with a request of 260 MB memory, you can allocate. Another process comes P5 with MB, then can you allocate memory for it? Yes, because you have 100 MB your free space, MB of space to P5. So what will be remaining? Remaining will be 50 MB of space, right? So this is how your memory allocation takes place in contiguous allocation. In the system, you will have two sections, operating system space and user space, and memory allocation will happen like this. At this time, each process will have a limit, address. In the initial section of this chapter, that every process will have a base register and a limit register which contains the base address and the limit address. So from where to where this process can access its memories, its instructions and data is specified using these two limits. So base is, so it is like you are sitting on this one bench, so that one bench space is only yours. So you cannot claim the other bench space. So that is like that. So you have to use only that much. If you are using some other space, that means you are trying to access an illegal memory access you are doing. You are trying to do an illegal memory access. You cannot access operating system space. You cannot access P4 cannot access P1 space. P4 cannot access P3 or P4 cannot access P5 memory space. So it has to restrict this. So for that you will be using the limit register and the base register as it is to check that it is using the same memory process. Apart from this resident operating system, there is another operating system which is the transient operating system, which I explained you yesterday. And I told you that the main core of the operating system that is minimum required for your normal execution or normal working of your system, your computer systems, that operating system is called the resident operating system, and it is always there in your RAM. It is always residing in your RAM. And when does this reside in your RAM? It is put into the RAM when you start your system. When you start your system, in your system you will always have an information of what location in your hard disk you have stored your, you have loaded your operating system. So when you are installing your operating system, you also specify to the whatever registers, that is a programmable read-only memory or whatever memories you all have, the read-only memory, there you all will be having an information of where the operating system is loaded in your hard disk, is stored in your hard disk. It pulls out the kernel or the core of your operating system and puts it at the beginning of the RAM. This is done by boot program, that is called as a boot program, and that is why you all will always be saying that my system is in booting mode. So when it is in starting mode, so when you press the button of the system and you say start, that time the boot program runs. The boot program is a program that is stored in a read-only memory which contains the information of which operating system you have and where it is stored. So that's why when you have a dual operating system, it asks you which operating system you want to load, whether you want to load Windows operating system or Linux or whatever operating system you all have. That is what is a boot program. So that program will be loaded here. Now this is the core. Now what is transient operating system? Transient operating system is part of this operating system that is not always residing in your RAM. It is loaded in your RAM only when that particular service is required. For example, you want to access your drive, your DVD drive. Then the DVD drive will not always be accessed. So why do you want that functionality or service code to be there in your RAM. Because you waste of your RAM space, right? So what we do is, when you say run your DVD, that time only that operating system's code that is there for handling the DVD drive is loaded into the RAM, and that takes care of reading and writing into your RAM. So that is resident operating system. The operating system code that is brought into the main memory only when its service is required is called as transient operating system. Transient because what is the meaning of transient? Getting in and getting out. When it is needed, you get in. When it is not needed, you take it out from the RAM. So that is why it is called transient, moving operating system. So transient kernel. We understood this, I won't go through this diagram again because we have understood that in the beginning of this chapter only, right? So for multi-programming, it is necessary that you have multiple programs in the RAM. So in this diagram, if you see that there are multiple processes in the memory, so there is operating system at the beginning. I told you why you need the operating system at the lower end, because of the interrupt vectors. Interrupt vectors always work with lower addressing. That's why keep the operating system at lower address bits. So that operating system and interrupt vectors work together, and hence it is better to always keep them operating system at lower bits. It's not necessary that you keep it in lower bits. You can also put it into the higher bits, means bottom of the RAM, not at the beginning of the RAM. So here you see that there are 3 processes in the first one. Process 8 finishes its execution and leaves. If you see the space that is allocated to these, P5 is allocated less space, P8 is more, and P2 is also less. P8 finishes its execution, and that is the space that is created, and that space, another process when it requires for a memory, the amount of memory that it requires, that is allocated, and the remaining is kept as empty, so that another process can utilize that space. So here again process process 10 has come and made a request, and that's why the remaining whatever space we had, free space, from that the space that is required for process 10 is allocated. So here in this free space is called as holes. Free partitions is called as holes, and this process wherever we have allocated, that is called as allocated partitions. So these are nothing but partitions. This is operating system partition, this is other process partition. This is free space because there is no process here, so this is called as hole, and these are allocated processes. So operating system has to keep a track of what is the free space, what is the allocated space, which space is allocated to which process, so that if a process tries to access an illegal memory, the operating system raises an execution error exception and traps and makes this process to exit. So operating system is mainly responsible for taking care of this protection of memory space of one process from another process, itself from other process. So here these partitions are not of fixed size. That is what you will understand from this diagram also. They are of variable sizes. So these partitions are looking at the same sizes. Not necessarily they are the same size. This can be of 512, this can be of 520, this can be of 500, so like that. So each partition is of variable length, variable partition, and the free spaces are called as holes. Next we understand the dynamic storage allocation problem. So when you are when you are having a RAM and you are having memory space, now as I explained here, that initially there were 3 processes, P1, P2, P3. Then new process came in with a request of 200 MB. Whatever process, the memory that we had was only 100 MB. So now supposing 2 processes come in, P4 and P5, can we allocate memory space for P4? No, because only 100 MB space is free. Again, P1, P2, P3 are allocated memory. P4 and P5 come into with a request for memory allocation. Can we allocate P4 memory space? No. Why? Because its request is for 240 MB and P5 requests only 50. So can we allocate space for 50? Yes. P5 can be loaded into the memory because only 50 MB is its requirement. Now, what do you mean by this Dynamic allocation means dynamic allocation at execution. So best fit, first fit and worst fit. First fit means whenever a request comes in, whichever is the first hole available, you allocate that space. Then as I had told you at the beginning, that operating system is there, no user process is there, all holes are free, the entire RAM is free. There is no partition. Okay, there is no partition right now. Consider that there is no partition. Now P1 comes with a request of 350 MB. Okay, supposing you have 4 GB of memory. Out of 3 GB, 350 MB. Smaller, that can better example. As 1 GB. Left over for your user processes. In that 350 is equal. So if you consider best fit, first fit and worst fit, this is free right now, so you can allocate. So this remains 900. So this is 524. Supposing now with 474. Right? Okay. Another left over 150 means 324. Right? Okay. Now there is 300 and these two fields are available. Supposing now another process comes, I'll take it less. Let's understand first fit, best fit and worst fit. 80 MB is P4's requirement. P1, P3 are there in the system. Free holes are 100 MB and 224 MB. Now, where will you put this P4? If we go with the first fit, who is the first fit? Requirement free hole is of 100 MB. First free hole. The first free hole is this hole and we can allocate that. Okay, so that is first fit. Best fit. Out of these two, which is the smallest hole that is good enough to, again it is this located here. Next, what is the worst fit? Is always out of the free holes that is available, you have to select the highest freely available. So worst P4. The P4 comes here. Okay. So there is a difference in putting P4 here and P4 here. Let me take one more example. Let me add one more slot to this so that it will become clear to you. 320 meaning suppose if process comes in and I allocate space for some process P5 which is requesting for 200 and 200 MB is gone. So 124 is remaining. Okay. So what 24. Okay. Supposing now this one. So this is okay. So rest is what is utilized. This is and first is a memory of 250 MB, free space of 100 MB, and third 24 MB of space. Request of 80 MB comes in. So now where will you put the first fit, best fit, and worst fit? So write the P4. Supposing I have P7 120 MB request, and I have P8 with 112 MB. Okay. So this is the requirement. 3 processes are there, 3 holes are there. So let's do first fit, best fit, and worst fit for this. Fit. First process that is requested is 80 MB. So where will you put this? 80 MB. First fit means the first hole, whichever is there, you will allocate that to it. So we'll allocate it at slot 1. Free hole 1. So at 1 you allow P4. P4 is done. Next request is from P7 with 120 MB. Where will you put it? You cannot put it at 100 MB because 100 MB is not enough for it. So you'll have to go in for 124 MB. So I will allocate slot 3 to process free hole 3 to process P7. Now P8 comes in a request of 118 MB, but it cannot be allocated because we are only having free space of 100 MB. This is first fit. Let's go for best fit. Best fit for 80 MB, which is the best fit, which is the smallest good enough slot for 80 MB process, 100 MB, because 100 MB is close to 80 MB. 124 MB is also more, but it is little more than 100 MB, and 250 MB is too big for P4. So we will allocate. Then next process is 120 MB, which is the next smallest hole that is available, that is good enough to hold P7. Process is, the hole is third. Third hole we will allocate it 7, which requires, so it is 124 MB and requirement is 120 MB. Next request is P8. P8 can be allocated the first hole which is remaining, and it is 250 MB. So this is P8. So this is best fit and first fit. Now let's see the worst fit. You will have to select the largest possible hole. You should come in the descending order of the holes. The hole size descending order. So which is the highest slot here? So 3 allocation at 250. Second process we should allocate 100. So in the worst fit will be assigned. So will to P4. In the second process will be P7 will be okay. Again, if you see P2, the whole 2 will remain vacant and one process will be in waiting state because there is no enough memory. So this is what is best fit worst fit and first fit. So this is how you all will be doing dynamic memory allocation. Now the problem with this dynamic memory allocation is two. First one, internal fragmentation and external fragmentation. First, what is fragmentation? Internal fragmentation and external fragmentation. Fragmentation means the space that is available in RAM but cannot be allocated to a process is called as fragment. Now here, if you consider best fit, first fit and the worst fit, whole 2 is not allocated. This is free space, right? This space is free space. Whole 2 is free space. Process P8 is waiting for allocation, but you cannot allocate it because it is not large enough to be allocated. It's only 100 MB and requirement is 112 MB. So it is called as external fragmentation. External why? Because it is not allocated to any process, it is free, and this process is not in hold of any, this memory is not in hold of any process. Now consider first whole allocated 250 MB allocated to P4. How much memory? P4 is of 80 MB. So P4. So out of 2 remaining 170, yeah, yes, 170 MB is allocated to P4, but it is utilizing only 80 MB because its requirement is 80 MB. This process is only 80 MB space requirement. So this remaining internal fragmentation. So but it's a free hole, but it is not good enough to be allocated to some process is called as external fragmentation. And but it is only free space that is allocated to P4 is a waste because it is a small process having a large space. It's like a big house with a few people staying. Wastage of space. So this is called as internal fragmentation and this is called as external fragmentation. So let's understand internal fragmentation and external fragmentation. So external fragmentation, total memory space exists to satisfy a request but is not contiguous. Another thing, it cannot be, it may not be contiguous. So that means that here there is some space. Here. There is operating system. So here process P1 is allocated. Then a few 20 MB of space is left here. Allocated here. The process P4. So this is the memory allocation. These are free. This free spaces is available and the total that 5 is totally 40 MB. So 30 MB, we cannot allocate that because it is not contiguous. It is because one process left from here and it requested only so much, so we gave that. So like that. So somehow is left over in between, and this left big enough to allocate to a memory, but it is not continuous. It is spread. It is spread in the RAM. The space is spread across the RAM in bits. So you cannot allocate to any process. This is called as this is external fragmentation. Was and we require 90 MB. So 90 MB is using the space that it is having is wasting. So that is called fragmentation. So internal fragmentation, allocated memory may be slightly larger than the requested memory. Allocated memory may be slightly larger than the allocated. Requested memory is slightly larger than the requested memory. Then there is an internal fragmentation. So first fit analysis reveals that given n blocks allocated, 0.5 blocks are lost off due to fragmentation. So if there is n blocks allocated, n processes. So here there are how many processes, how many blocks? 1, 2, 3 and 4. 4 blocks if there are allocated. Out of that 4 blocks, they say in 50% margin, 1/3 of the blocks will be not used. It will go to, it will lead to fragmentation. 1/3 of the block of 1/3 of this entire memory that is allocated, that in that if you consider 50% rule will be wasting, then 1/3 of the blocks will be wasted. So the first fit analysis reveals that given n blocks, so if you have n blocks of memory allocated, then 0.5 blocks are lost to fragmentation. So 0.5 blocks, these blocks are lost to fragmentation. We cannot use them. So what is the solution for fragmentation? The solution for fragmentation is compaction. What is compaction? Compaction means this you all can do it in your secondary storage device on your system. We go on storing files into different locations and then we go on deleting those files. So this deletion of files will make the empty spaces in between our hard disk. The memory that is available in your hard disk. Supposing you keep you store the first file here, you store the second file here, you store the third file here, fourth, fifth, sixth, like this. In continuous memory locations, it goes on storing. So wherever is the next free space available, it will store there. Supposing now you don't want this file, so you delete this file. Then you don't want this file, so you deleted this file. Okay? So this space is available, but it is not utilized because the space that is available is too less for your new file to be stored. And it shows that there is less memory space. What you do is, you do compaction. What do you mean by compaction? Defragment also it is called. Compaction means the files will be moved. So two files were moved, so two spaces are now, continuous memory is kept free. So whatever memory space was in between that was free, that we have put it at one side, and all files we have rearranged it at another. Means copying and pasting the files one after the other, rearranging the files. This is what happens in your home also. When you have a cupboard, if you throw the clothes and keep it unorganized, then you don't have space. But if you organize your clothes, you will see that there is more space in your cupboard. The same thing applies here also. So compaction means putting the files. So if I put all these processes one after the other, so instead of keeping this space free here, I will move P2 up. So this free space and this free space now combined. This also gets added up, and I will move P4 up. So that means the free space that was there will all come down now. So total 40 MB space will be here, and all this will be free spaces are occupied by P1, P2, P3 and P4, and the free space is here. This is possible only when you have a dynamic readdressable memory. The memory is dynamic. Reallocation of memory is dynamic. That means you can move the processes in the RAM. It will not harm. If there is static binding of addresses, then remember, static addresses means this address is binded to your process. So this space has to be there with P3 only. It cannot shift anywhere in the memory. So if dynamic memory allocation is done, that means during runtime you can change the memory addresses, then only these processes can participate in compaction. Otherwise, they cannot participate in compaction. So shuffle memory contains to place all free memory together in one large block. So shuffle all the processes so that you get one free block at one part. Then compaction is possible only if relocation is dynamic and is done at execution time. So if these memories are readdressable at dynamic time, execution time, then only you can do this compaction. Otherwise, you cannot do compaction. Another problem that you have to take care is I/O. Again, I/O is a problem. If a process was waiting for an input or an output status to receive back, then you should not move those processes because they may be working on that particular memory buffer. That memory that was allocated to that process, in that one part of the memory is allocated to buffer, I/O buffers. In that case also you cannot do this. So you cannot do compaction. Latch job in memory while it is involved in I/O. So what you do is you latch that job, that process in its place until it does not finishes its I/O. So this latching is possible. You can do that latching. So do I/O only into OS buffers. Best solution is to do it in OS buffers. Now consider the backing store has the same fragmentation problem. So remember that this is main memory, and on our hard disk we have our blocking store, backing store. This backing store also will have the same problem. That is internal and external fragmentation. There also you can do compaction. Next is segmentation. What is segmentation now? Segmentation is basically how a user view and the actual memory allocation are two different. User sees from the point of view of a program. So he says that your program has main memory, main function, has one IO.h has functions defined, right? So all these are different functions, and this is one big program, and in this program we see it as in function 1, function 2, then we see it as library files or built-in functions. Okay, so apart from this, it has stack, it has a symbol table. What is symbol table? Symbol table is the table for the variables that you have declared. Each of these symbols will have an address and it will have a value stored in that address. So that is a symbol table. So all these are different modules of your program or your process, and we see them as subroutines or segments. So segment is a logical unit such as main program, procedure, function, method, object, local variables, global variables, common block, stack, symbol table, and arrays. If you consider a C program, the C program itself has memory. If this is allocated to your program like addition, your addition program addition.c, then this itself is divided into code section wherein your actual program code is stored. Then you have the heap. Heap is the memory from where you do malloc, calloc, dynamic memory allocation. So that is from heap. Then you do function call and all that. So for that you use stack. Even your local variables are stored in the stack memory. Then you have global variables. The global variables are stored in global memory. So these are the different segments of your C program process. So the exe will have these many segments. So, and data will be stored from there, and all execution of the instructions is done by referring to these memory locations and data stored in these memory locations. Apart from this, this is what is user view. That's what I'm saying. This is user view. But actually, the user view, if you see that this is the logical addressing, but if you see the physical addressing of it, it will be like this. These modules will be stored in physical memory space in this way. So first module or segment is stored in the first hole, second is stored in the fourth or fifth hole, then third is stored in the sixth hole, and fourth is stored in the second hole. So in this way, the logical addressing and the physical addressing is different. So we have processes, we can divide the process into segments, and we can put these process segments into different holes in your memory. So what all we require? How we are going to address these locations? To address these locations, you will have to check out which segment, this function, whatever functions is there. For example, I consider this as one segment. In this segment, if I am going to, in fifth instruction I have to execute. So I have to see this segment is stored at which, what is the segment number? In that segment, this is the offset. What is offset? The location where my instruction is. That is the offset. From the beginning of this segment, what is the distance of this instruction? That is the offset. So you will have two information, segment number and offset. So segment number is, supposing in this stack, I want to access the fifth position element. So from the beginning, I'll have to go to the fifth location and access that. Okay. So symbol table also same. From the symbol table, I want to access the 10th symbol, then the offset is 10. Are you understanding? So that is offset. And each of these is having a segment number. Supposing this is segment 1, 2, 3, 4, 5, 6. So what will I address? The 10th symbol that is there in symbol table. I will say it is in segment 6 at offset of 10. If I want to access a second instruction of this function, then I will say 2 means it is present in second segment and at an offset of 2. From the beginning, second instruction. Here, if I instruction, then I will say segment 3, sixth instruction. So that is what we will be doing. So we have segment number and offset. So segment table maps two-dimensional physical address. Each table entry has a base and a limit register. So each of these will have a segment limit register and a segment base register. Each segment will have its base and limit because each of the segment is stored in a different hole. As you have seen here, each segment is stored in a different hole. So if I want to access third segment's fifth instruction, then I will have to check which hole it is there in. So you'll have to map the segment number and offset. So for that segment number has to be mapped to the hole of the main memory, the frame at which it is stored. That then access the offset. So if I want to access third instruction from the third segment, then I'll have to go to this frame, this hole, which is this hole number, that is first, second, third, fourth, fifth, sixth hole. In the sixth hole, I will have to go to third instruction. So third segment is stored in sixth location of your main memory, sixth frame. So I'll have to go to sixth frame, third instruction in that frame. So for that, you will have the base register and segment base register and segment limit register, and your address, logical address should be less than your segment limit register. If it is less than the segment limit register, then only it is a valid address, otherwise it's not a valid address. So we can understood this logical to physical addressing can be understood with this diagram. The CPU generates segment number and offset in that segment, which instruction it wants to execute in that particular segment. That segment number is checked for what is the base at which segment, which location that is stored, and the offset is checked whether it is less than the limit register. If it is less than the limit register, then we will add the base register and access that memory location. If that offset is more than the limit register, it means that you are trying to access the memory location of some other segment or other process, and hence a trap will be generated. Next is paging. Another very important concept is paging. So paging means, now if I have a process divided into segment, the entire process is divided into So if you have a process, supposing I have a MB of process, okay, and my page, this is page 4. The problem with the first two sections was, that is contiguous memory allocation, was that you needed continuous memory allocation done for each of these processes. One process required an entire memory. Whatever is the total memory that it was requiring, we were putting there. Even segmentation also, we had segments, and each segment had to have a single memory allocated to it. Entire segment, however big or small that segment is, that much memory was needed for each of these segments. But what we can do is, now the best option is to have your process divided into segments, into pages, and your main memory also divided into the same size frame. Whatever is available, the thing, you divide it into equal size frames. Now what will be the advantage? Your page and your frame, so these are called as pages, and these are frames. The operating system memory is divided into frames, and your process is divided into pages. So each of these pages are of same size, and the frames are also of the same size. What will happen now? Here, you put this page here, you put this here, there is no problem. Any page you put into any frame where it is free. All are of equal length. Are you understanding? All are of equal length. Now there will be no external fragmentation here, because external fragmentation is eliminated because the page size is equals to the frame size. There can only be internal fragmentation. How can there be internal fragmentation now? Internal fragmentation can be now 500 is a 2 raised to it equals 5. But if I of memory my process was 520 MB. Supposing each page I allocate 4 bytes. So out of 5, how many pages will require? 128 pages. But for how many pages are required? 4 again. 4 ones are, so 4 threes are 12. Okay, this is an even, so that we get a fraction value. It's undivided by 4. 518 divided by 4. So 4 ones are again. 1 remains. 4 to the 8. 8. 4 remaining now. Because 4 nines is 36. So how many pages are required? Each, and I will require one more frame. So totally I will require 100 frames. So now the frame in which the last page is inserted, the page, so totally how many pages I have? 130 pages I have. All 129 pages are the size of the frame. They are of 4 bytes. But your last frame is of 2 bytes. And your frame is of how many bytes? 4 bytes. So how much will be the internal fragmentation? 2 bytes will be the internal fragmentation. So that is what you need to understand. So there will be no external fragmentation if you use paging, but there can be the internal fragmentation for such sections. So internal fragmentation, if it is only, if it was for example 512 or 516 and it is 20 or 517. How many bits would have been remaining? Only 1 bit. For 1 bit, 1 frame has to be given. So this is looking very small right now because we have considered a 4-bit this thing. Page size and frame size is 4 bits. But if you consider examples which are having page size which is in terms of MBs, then if you will realize that there is a large amount of space that is wasted in internal fragmentation. If there is a fraction which is in MBs,